How good was my introduction? Auxiliary angle is just another way of rephrasing questions that we're not sure how to deal with in other ways, so that they look like questions you already know how to solve, and then you can deal with them. Okay? So in order to get at this question, I want to consider this graph, the one that we looked at just now under revision. Except I just want to think about what it looks like. Okay? Now let's draw this, just roughly. Let's just sketch it out. Usually we draw things from 0 to 2 pi, but today, to illustrate something unusual, I'm going to go double that domain, 0 to 4 pi. Okay? So let's sketch it out roughly. At the beginning of the year under further graphs and locus, we looked at what happens when you graph things that are made up of two other things, right? So we use addition of ordinates, right? Now that's not always the best method, but here, because these graphs are periodic, they repeat, it's kind of a good way to go. So draw in roughly, maybe if you have some other colors, that might help. Draw in y equals sine x, and draw in y equals cos x, okay? And don't forget, we're going 0 to 4 pi, so that's 2 lots of both. Alright, now, it doesn't need to be beautiful. It just needs to be close enough so that we can notice a pattern. So in blue, I've got cos, and in red, I have sine. So, think back to addition of ordinates. How do we usually go about this? You think about the easy to work out parts first, and then you sort of fill in the dots based on the parts that are easy to determine. So for instance, up here at the beginning, okay, sine's equal to 0 and cos is equal to 1. 0 plus 1 is 1. Okay. In the same way, here at pi on 2, right, cos is equal to 0 and sine's equal to 1. So that's also going to be 1. Now in between, it looks to me like you've got these values that are both going to add up to something above 1. So it's probably going to head up a little higher. How high? Not entirely sure, but a little bit higher. Now, somewhere in between here and here, there's a point where the red's positive and the blue's negative. They should be equal, right? So when you add them together, they're going to cancel each other out. You should get 0 somewhere in there. Right? And you probably notice the same thing happening over here. 0 minus 1 is going to give you minus 1. Another 0 and minus 1 gives you minus 1. And in between here, just like this went above a little bit, there's a bit of a crest, you're going to get sort of the reverse happening over here. And by this time, you're probably starting to see a bit of a pattern. Okay? Let me try and, yeah, question?
Can we double?
No. And we'll see why, well, okay. What will, sorry, yeah, okay, so double that. So in terms of scale, I'm a bit off. Okay, but it won't go all the way up to, yeah, okay. All right, thanks for picking up the scale. Same deal then. All right, so let's try and connect the dots and see what's going on. Okay. This is going to come up, come down, head back up. Now, by the looks of things, again, I'm going to go through somewhere through here. There'll be one, up above here. There. Okay, this is going to go through here and here. Okay, so it's not pretty, but it's enough for us to notice something. Namely that, when you take sine and cosine, right, and you add them together. Sine and cosine are what we call wave functions. They're called wave functions because the shape of it looks like a light wave, a sound wave, a water wave. They all behave in the same kind of way. When you add together these two wave functions, sine and cosine, blue and red, what you end up getting is, well, another wave function. But it's different. How is it different? It's bigger, okay? So a more technical way of saying that is that the amplitude is greater, okay? So the amplitude's changed. But not only has the amplitude changed, sine, right? It starts off at 0, right? So it starts off right at the center. And cosine starts off at 1, so it starts off at those extremities as far as it can go. But our new one, it doesn't quite start at the center or at the ends, right? It kind of starts in the middle, right? So what does that mean? Not only is the amplitude changed, right? But also it's been phase shifted, okay? How much has it been phase shifted? Not entirely sure. But it's different in amplitude and phase. That's the important thing. Okay, now, we just said just now, we're like, well, it's kind of different, but we don't know how different. So I wonder, based on what we already know, what we've learned this year, for instance, okay, how could you work out what kind of, like more precisely, what graph is it? What's it actually equal to? Well, if it's different in amplitude, okay, what number determines the amplitude of a wave function? It's gonna be the coefficient, right? Yeah. This number out the front. In this case, they're both 1. Okay, so that's why the amplitude of blue and red are both 1. Okay. What about the phase? What determines the phase? What number do I have to adjust? Yeah, I have to sort of modify this, don't I? Right? Maybe like x plus 90 or x minus 90 or whatever. Okay, so that'll move it back and forth. So therefore, here's what I'm going to suggest. I think that sine x plus cos x is equivalent to, now I could pick either, but just for the sake of simplicity for now, I'm going to pick a sine function that's different in amplitude, so that coefficient out the front, like you told me, is different, and it's also different in its phase, so it's been sort of nudged a bit to the left or to the right. Okay. Now my question is, what would these two numbers be? Okay. Now, there are two ways to work this out. The first way is to draw back on, well, most recently we've been spending a lot of time on calculus, right? How could you use calculus, differentiation, stationary points, to work out the amplitude and the phase of this thing? Yeah?
Find the maximum of sine x plus cos x, and that's your amplitude.
Good. So if I could work out where this stationary point is, okay? Number one, the y-coordinate ought to tell me the amplitude. Number two, the x-coordinate ought to tell me something about its phase shift. So let's work this out, okay? If that's y, dy and dx is equal to, okay, nice simple functions. What do we get? What's the derivative? Sine turns into cos. Cos turns into minus sine. Okay, now remember what I was after was a stationary point. Don't forget, there's an infinite number of stationary points. Okay, so I just want the first one. That'll do. That's enough to work out these two bits. Okay, so I want to let it equal 0. Okay, so let's go ahead and solve this. Cos x minus sine x is equal to 0. So sine is equal to cos. Okay, sorry, it's a bit messy. Okay, so tan is equal to 1. What's the first answer to that equation? 45 degrees or pi on 4. Okay. Now I'm going to encourage you to try and start thinking more and more in radians as you can. Mainly because you're pretty good at degrees.
Yeah,
okay. So pi on 4. Yeah, thank you. Okay. All right. So let's think about this. X equals pi on 4. If I want to work out this amplitude, I need to know how high I am, right? So how do I do that? I'm going to take this and pop it into my y equation, right? So at x equals pi on 4, right? What's y equal to? Sine pi on 4, which is exact angle, 1 over root 2, okay? And cos pi on 4, which is the same, okay? So put your fractions together, divide through, that's my y value, okay? So what's that saying? This point up here is pi on 4 root 2, okay? So that seems to suggest at least, right, this r, this amplitude, that's 1.4, whatever, okay? Root 2 sine. Now, this phase is a little bit trickier, but think about it this way. I was thinking in terms of sine, right? If we just think about normal sine, this red curve here, right? Where does it usually have a stationary point? Usually. It usually has a stationary point at 90 degrees, at pi on 2, okay? But this is telling me it's not at pi on 2 anymore, it's at pi on 4. Was it pi on 2? Now it's moved over to the left, pi on 4, okay?
Oh, it's the average of it.
I've been moved from 90 to 45. So 45 degrees to the left, right? Or pi on 4 radians to the left. How do you shift something to the left?
Yeah, it's fine.
You add. That's confusing, isn't it? Right? If you remember, say a graph like that, to move it over to the left, you say y equals x plus 1, all squared. And then your root's at minus 1, which is to the left. Okay. So if I want to move this graph to the left, pi on 4 radians, I add pi on 4.